Hello, welcome to the session on cyber-physical systems. I believe Ram wanted to give a short introduction, and then we will go right into the talks, and then followed by questions. So welcome everyone, and Ram, if you
Okay,
want to go.
let me bring up my slide. Can you see my slide?
Yes.
Yes.
Okay. All right. Hello, everyone. It's a pleasure to see you all virtually for the moment. So as Christian mentioned, so Christian and I are the team leaders for the Cyber Physical Systems team. I'm from the School of Informatics at the University of Edinburgh. Christian's from the Mathematical and Computer Sciences School at Heriot-Watt University. Both of us come from, broadly speaking, the area of robotics. But I want to start off by saying that cyber physical systems is quite a bit broader than what one normally understands by topics such as robotics or human-computer interaction. So just to set the tone for this special session, I wanted to kind of recap what we think of as cyber physical systems. And in our conceptualization, we are interested in various kinds of mechanisms where an algorithm is doing some part of the decision making. And there's importantly a tight integration between what's going on the physical side in terms of actuators or some kind of a decision that's having an effect in the external world, and the software side. And we tend to be interested in small systems, large systems, so a variety of spatial and temporal scales. And we are particularly interested these days in systems where the behavior might include not just a mechanical component, but also a human component. So the examples of cyber physical systems could range from robotics and avionics systems all the way out to sort of medical devices, and on the very large scale, smart grids and infrastructure at the national scale. So these are all cyber physical systems. But then that might sound like we're just talking about computer science in general. So to give you a little bit of a flavor for what is going on in this space that's kind of pertinent from a research point of view and from a social applications point of view, we are thinking about the emergence of a variety of automated decision-making systems that now have arms and legs in the real world. And we are quite interested in issues around, safety, verifiability, and trustworthiness. And these are becoming especially important when we start applying these kinds of systems in domains such as healthcare, for instance. I mean, the fact that we are all sitting on different ends of a computer and we can't physically see each other, it's completely because of healthcare issues. And then it's interesting to see that despite all of the development of technology, society is a little bit caught out by our inability to cope with a pandemic such as this. And so I think this is a very apt kind of description of the kinds of problems that CPS should attempt to tackle. So to give a flavor for some of the ongoing activities within CPS, so within the context of SIGSA and the Scottish universities, we have some very strong groups and laboratories in the area of robotics. So both Christian and I are part of the Edinburgh Centre for Robotics, which forms a kind of basis for many of the activities that we are doing within SIGSA as well. But it's not only robotics. So we are trying to reach out also to strengths in the area of human-computer interaction and artificial intelligence and machine learning more broadly. And the themes that are kind of emerging and becoming quite interesting in not just from a scientific point of view, but in the ways that we are able to engage more broadly, I want to mention one or two. So we are engaging in a number of new projects in the area of what would be called trustworthy autonomous systems. So this is a big UKRI team, and several of us are engaging with initiatives like that. And that very much fits with the remit of what we are trying to do within CICSA and within cyber-physical systems. Another theme that is becoming increasingly more important is the idea that computer science really is only one piece of a bigger puzzle when we think about how CPS fits into our society. So we are engaging quite heavily with colleagues in a number of different areas outside of the computer sciences. So this includes the Edinburgh Futures Institute, our colleagues in law and social sciences, and all of this is driven by the idea that ultimately the computer has to sit within a human-centered view of how society functions. And that's sort of the theme of how we have the CICSA conference today. So with that, and without further ado, I'd like to hand over the stage to two of our colleagues who are excellent examples of exactly the kind of themes and kind of questions I've just mentioned here. Thank you.
Thank you very much, Ram.
Yeah, I will stop sharing
and I believe our first speaker is going to be.
You should have control back, I think.
Rick, are you there?
Yeah, I'm here.
Perfect.
Okay, so should I start?
Yes, please. If you start sharing your screen,
Let me share
and then
my screen. Okay. So you can see
that
the
looks
screen,
good.
right?
Thank you.
Okay, great.
Yes.
So hello, everyone. I am Rick from University of Edinburgh. I work on information processing and machine learning related to cyber physical systems, robotics, sensor networks, and various other things. I work a lot on processing and learning from data about mobility. It can be movement of robots, movement of people, and various other kinds. So all this comes into play in this project, where we will talk about targeted interventions for pandemic control with focus on COVID-19. This is less computer science and technical in the sense that we will not be developing algorithms, protocols, but all this is based on cyber physical systems data, as you'll see. And our question is, how does mobility influence the pandemic and what can we do about it? So this is joint work with Haotian Wang at Rutgers, Abhirup Ghosh, previously at Imperial, currently at Cambridge, Jiaxin Ding at Shanghai Jiao Tong University, and Jie Gao at Rutgers. So the situation is this: we have had COVID since December 2019, and we have had to put in large-scale lockdowns in various countries to get a hold on the situation. The result is that GDPs have dropped. You may have seen this plot in various places. India has dropped by 25%, UK by 20%, Mexico by 17%, various other countries by fairly large amounts. Jobs have been lost in hundreds of millions. And it is projected that due to this job loss and disruption of the labor market, essential industries like food and agriculture are being disrupted. So while all that has been going on, infections and deaths continue to rise. We do not really have a hold on the situation, except that we are going in and out of lockdown in various forms to try to control the situation. But meanwhile, 34 million people have been infected till now, 1 million people have died. The question is there a better and less disruptive strategy? Because it's not just a matter of this, the number of infections. As we saw, people are losing jobs and livelihoods, and the whole economy is being disrupted. So we started thinking about this, and one observation is that movements are critical to the spread. So the picture you see on the right is the global airlines network. And the point is that that is how the virus spread, right? So starting from Wuhan, it spread all over China, it spread all over the world. It is mostly because people with the infection carried the virus with them. If nobody had moved in all this time, the virus would never have gone anywhere. Incidentally, I think on XKCD or on one of the books by Randall Munroe, there's an interesting thought experiment about what happens to an infectious disease if nobody ever moves. But that is not our focus. The point is that the spread of the virus is closely related to travel and mobility. And several studies have shown that this is, as you would expect, more travel implies more infections. In regions where people move a lot more, the virus spreads a lot more and you get a lot of infection. So all that is kind of intuitive. And if you think about it, these lockdowns are targeted to actually cut down on this movement of people, except that it seems to be locking down all movements equally. And our question was, are all movements equal? Do we really need to restrict all movements equally, or is there a more selective strategy? So for that, we did simulations on some real human movement data. So on the right, I have drawn by hand some random movements as it might occur, some trajectories of people. And we asked the question that given this sort of data of several moving people, how does the movement determine infections? Do individual movements matter? Do individual meeting places matter? So in this case, the meeting places are these junctions where two trajectories meet, two people meet with each other. And the question is that, are these points important where people meet in classrooms, in cafeterias, in restaurants? Well, of course, they are important. The question is how important and which ones of them are important. So in that respect, our question is, can targeted actions be more effective than what we have been doing till now? Can we reduce the social cost we are paying in terms of economy, livelihood, and general lack of social interactions? So our main observations are that from all the studies that movements are heterogeneous. Everyone moves, but not everyone moves equally. There are few people who move a lot and lots of people move relatively less. We also find that the spread by human movements is different from standard epidemiological models like SIR or SEIR. The point of this is that when the virus is spreading by movement, like in this case, basing your inferences on standard epidemiological models may be inaccurate. We have to consider actual movement of people. We find that large-scale lockdowns are costly, which we already know, but I will show you later that they do not quite get you proportional benefits, but they can be useful. For example, they can be useful to gain time. And we find that a few highly mobile people and a few popular venues are critical to the spread. They kind of determine the early infections. And based on these observations, we can suggest this kind of interventions. That is, if you're going to take interventions, take action on the highly mobile people. People who move a lot are decisive if you're trying to control the pandemic. Actions on high popularity places are effective. Places where lots of people visit, like university cafeteria or a very popular restaurant may be the place where you want to be more strict about things than other places. And if you can do these things, that can achieve a lot of reduction in infections while retaining a lot of your social activity. So we measured all these things in our simulations. Finally, there's a type of intervention where you group people. So for example, in a school, you can create cohorts and you make sure that people from different cohorts never meet each other. So, and any infection in one cohort will stay restricted within that. What we found is that, yeah, in principle, this can work, but in practice, this is very difficult to implement well, which is not very surprising, but we'll discuss that later. Okay, so those are our conclusions. So let's see how we went about getting to them. So we set up a simulation. We adapted the SEIR model to adjust for COVID behavior. Like we introduced the possibility of asymptomatic carriers and such. And we also included the possibility that other than the infection transmitting from a person to a person, it can transmit to a venue, and that venue can infect a person visiting there. The argument for this is that, as we know, COVID infections can be left on surfaces at a venue, and someone touching that can get infected later on. Or you can think about infection being retained by the air conditioning system with a closed loop. Or simply people at a venue like a bartender or a security guard may be infected, and they might infect other people coming in later. So either way, this venue forms a static point of collecting infection, which can infect other people going there. So that is the simulation setup. And then we run this on the actual mobility data. We used 3 data sets with different forms and scales. The first is a set of Foursquare check-ins. So these are check-ins that people had made on Foursquare and then made public. And some other researchers previously at University of Freiburg, Germany, had collected all this, and these data sets are available publicly. So on the left, you see here, let me see if I can. Yes, on the left, you see here the data set for 7 different countries all over the world. So they contain like millions of check-ins from thousands of people and thousands of venues. And we used a couple of other data sets where we used data from Tsinghua University Wi-Fi connections. So they did this study several years ago to evaluate the Wi-Fi connectivity in the university, but it contains information about who connected to which access point at what time. This data set is not public. We got it from the researchers. But they do let us check how many people were at a particular venue at a particular time, and that lets us simulate the spread of infections. Similarly, we use this bike data set from the Zhengzhou city of China, where we have GPS traces of rental bikes. So these 3 data sets lets us do kind of 3 different types of things. The Foursquare one is very good for checking the effect of venues getting infected. The Tsinghua data set is very good for checking things like large numbers of people meeting at different places. And the bike rental data set is good for testing more amorphous, just GPS traces from people. So first we tried out what we would call the blanket lockdown, the type of lockdown we are seeing all around us, mostly that everyone is encouraged to stay at home. And we simulated that by simply removing 80% of all events at random. So for example, we in the check-in data sets, we removed 80% of check-ins. In the other ones, we removed 80% of the meetings that occurred. So we did not allow infection to transmit on those meetings or check-ins. what is observed is that it delays the peak. If you do this blanket lockdown thing, it definitely delays the peak, but which we see, for example, around here. But it does not necessarily reduce the total number of infections. So this left-hand side plot is the cumulative infection plot, and that doesn't seem to drop too much. Similarly on, so this first one is on the Foursquare New York City data set. The second one is actually on a university data set, and in fact doing a slightly different experiment. But the results are similar, that the peaks can be delayed, but the total number of infections don't change too much. This is true in these two cases, but I should mention that in some other cases, the results are a little variable. Like in some cases, the infections do drop a little bit more. But in general, the warning seems to be that it might not. And these vary a little bit depending on exactly when you are making the intervention, exactly how long you are doing it, etc. So the top figure, in fact, is about when you're making the intervention. And one of the interesting things there is that an early starting intervention is not necessarily very useful. If you start too early, you can try this out as a thought experiment in your head. If you start, for example, too early, you might do all your lockdown before the infection is really spreading. And then when the infection really starts to spread, you don't have too much ammunition, because strict lockdowns cannot be sustained for too long. So the point of all this is that this blanket lockdown can be useful in delaying the peak, gathering resources in that time, that kind of things, but needs to be done with some care. The other thing we did is that we compared with the SEIR model, which is the susceptible, exposed, infected, and recovered model. A standard epidemiological thing, but where the infections are transmitted at random between people, homogeneously at random. And the observation is that in the mobile case, which is shown here in orange, we get a total less number of infections, but in the mobility-based simulation, the infection rises earlier. Whereas in the SEIR model, where infections are completely random and you don't necessarily infect people near you, you just infect anybody, infection takes a longer time to rise, but the total number of infections in the end is larger. Okay. Also, the peak is larger in the SEIR model and it occurs later. The point of all of this is that when infections are carried by moving people and transmitted to nearby people, as in the case of most infections, the behavior is actually different from the standard SEIR model. So we really need to keep an eye on the data for these things. Okay, so we need to study mobility a bit more to understand what really is happening with these mobile infection carriers. So first observation is that mobility is heterogeneous. Check-ins or meetings per person, if we plot the number of people having a certain number of meetings, that seems to follow an exponential-like distribution, meaning that most people have relatively small number of meetings, but some people have, a few people have large number of meetings. Similarly, the number of check-ins also follows similar trends. Only a few people have lots of meetings or check-ins. Most people have relatively few check-ins. If we count check-ins per venue, like how many people visit a venue, that follows a more power law-like distribution, meaning that there are a significant number of hubs in this distribution. There are many locations where lots of people visit. So our idea was, okay, so let's see what happens. So with these highly active people and highly active venues, are they playing a significant role? Because in general, in social networks, hubs are known to play an important role in transmission of information, infection, etc. Exactly what happens with this mobility scenario? What we found is that highly active people and venues do influence the spread. In particular, we find that the very active people tend to get the infections earlier. So they push the early exponential rise in infections that you see. So in this case, for example, this green curve is the overall population. The blue and orange curves are different fractions of most active people, and they reach earlier peak, and a larger fraction of them is getting infected. This is in New York City. This is in Istanbul. Similar patterns hold. This is in the university data set. This is in the bike data set. Essentially, similar patterns hold in all these cases. I'm sorry, okay, yeah, so the other point I should make here is that similar patterns also hold for the most popular venues. I'm not showing the plots here, but most popular venues are more likely to infect people and infect them early. So the natural strategy is that we should act on the most active people. If you can isolate, for example, the X% most active people, that can have a large effect, it would seem. So we tested that, and it does turn out to have a large effect. So here you get the results for what happens if you have no mitigation, what happens if you isolate 5% of people, what happens if you isolate 10% and 15% of people. And what you see is that the cumulative plot, the total number of infection does drop rapidly as you isolate the top few most active people, and the peak gets delayed and it gets lowered. This plot is about the social value. We are measuring how many of the meetings are retained, and we find that actually something between 80 and 40% of the meetings are retained under these measures. You'll remember that when we were looking at 80% lockdown thing, we were not getting a significant effect in the total number of infections, but the social value was lost a lot. This was dropping to 20%. So similar with the bike data set also, that if you make a 5% to 15% intervention, the number of people getting infected drops quite a bit, and you do not lose a lot of social value. Similar things can be done on the most popular venues. What if you close down the most popular venues? In this case, actually, the effect is even more dramatic. If you close down something like 0.1 to 1% of the most popular venues, for example, in New York City, the peak drops rapidly and the total number of infection drops rapidly, but the social value does not drop that much. So this is at something like 80%. Similarly, in Istanbul, the social value seems to drop a little bit more, but the peak does drop reasonably. Okay. So we thought, okay, let's make a more precise comparison of how much of health value we can get. That is, how many people can we save from infection while retaining how much of social value. So we define social value as the fraction of check-ins or meetings from the original fraction that are retained under a particular intervention. And health value is the number of people that were saved from infection to the number of people who would have gotten infections without an intervention. The point being that these are designed so that higher health value means fewer infections, higher social value means more social interactions. So the plots we get for that are something like that. Here, everywhere on the x-axis, we are plotting the social value. On y-axis, we are plotting the health value. We are comparing staying home, which is your blanket lockdown strategy, with closing popular venues, closing random venues, protecting random people, like isolating random people, and protecting active people. So the observation here is that on the New York City data set, with the closing of popular venues, we can get 80-80 trade-off. We save 80% of people while retaining 80% of social value. In the Istanbul thing, it is a little worse. By closing popular venues, you get 60-60. The thing to observe here is that blanket lockdown is much worse in comparison. To get a high value on any one of those, you have to compromise a lot on the other. Similarly, in the university data set, it turns out that the protecting the active people is more effective. kind of, because this is more about meeting between people, we are focusing less on the venues. And once again, you can get something like 80-80 here, similar with the bike data set. So the exact numbers, as you can see, varies a little bit depending on the exact form of the data, the form of interaction, etc. But the point is that these targeted things do seem to have good effect. So we also tried out what we call the grouping strategy. That is, you divide people into cohorts to make sure of minimal cross-cohort interactions. The observation is that this does slow down the spread because infection from one cohort cannot get to the other cohort. And it works reasonably well for small populations. It doesn't work so well for large populations. It seems that it can work for large populations where you need large number of groups. This is something that needs to be studied more as to what is the right number of groups for a population. We are not quite sure. It can be something like log n or square root of n. We are not sure, but something sublinear in n. But the problem is that this strategy has lots of drawbacks. So large number of disjoint cohorts are hard to implement. So in our simulations, you need at least 4, 5, 6, 7 cohorts for it to have any useful effect. And that number of cohorts are difficult to implement anywhere, for example, in a school. It is hard to maintain consistent cohort across various domains because you have to maintain some consistency in the separation people have in work, in school, at home, because otherwise the infection is just delayed by a day. But then it's not clear how you can maintain consistent cohorts across very different domains. And of course, this loses quite a bit of social value at boundaries because any cross-cohort interaction is eliminated. Okay, so that is what we have for results. Some quick discussion and thoughts. So we talked about actions on most mobile people. The prototype way of doing that would be isolating people, but that is, of course, not the practical thing. You cannot ask the most mobile people that you guys have to stay home. It might also not be practical because these may be some essential professions. So, but what we may be able to do is we give them better protective equipment. We put stricter regulations on those industries, or we do more frequent testing. We give them vaccines earlier, that kind of thing. That is, instead of isolating them, we can perhaps protect them better. And then if they don't get infected, they will not spread infection as much. Similar with popular venues. It is perhaps not practical to just close everything down, but maybe we can have stricter social distancing rules for those. Maybe we can have different modes of operation. So on the right, the pictures show what happens when you close different places in a university, like closing classroom versus closing cafeteria, etc. And as you would expect, something like cafeteria, where lots of people come at the same time, has a large effect if you can close it. But people have to eat somewhere, so maybe different modes of operation, like giving packed food, can be useful in things like cafeteria. Another thing we tested, but I don't have the plots here for that, is frequent cleaning seems to help for the case of transmission through venues. So like even cleaning meticulously once a day and maybe ventilating the air properly can have effect as far as the transmission through venues goes. The other thing to observe is that in all of this, the trends are consistent, the numbers are not. So sometimes something saves 80%, sometimes it might save 60% of infections. But what is consistent is that the hubs, the most popular people and venues, consistently have strong effect. So all this seems to be somewhat dependent on the type of interaction, the type of data. So we should, and this whole thing needs a lot more study to understand better, because simply mobility of people is not itself a well understood topic. So until that is clear, we should rely on the trends that this sort of action can reduce, but not on the exact numbers. Similarly, we need to study better the effect of scales. So the New York and Istanbul data showed that closing 1% popular venues has a very large effect. In practice, it is possible that with larger number of venues and larger number of people, it will need to be a little bit more, maybe 10%, but the general trend that the most popular venues are critical should hold there as well. The last set of points is that the blanket lockdown we saw is expensive, and it can be used, but we should know why we are doing it. It can be used for strategic purposes, like you use that, like we saw, to delay the peak, which it can do very effectively, and you build up resources and medical supplies in that time. There are things called spillover effects that needs to be studied. Basically, it is known that infection in one region is affected by behavior and mobility of people in neighboring ones, because those people are likely to come into this region, or of other places from where people travel frequently. So these spillover effects need to be studied, and there have been papers basically saying that it is not enough to take action inside, for example, a city or a district. These actions need to be coordinated at a national scale. Something about privacy, which we did not discuss at all. We have recently been doing a lot of research on privacy and how to get privacy preserving data from cyber physical systems, and how to make privacy preserving machine learning for cyber physical systems. That whole thing is very important here because we are dealing with people's data, but how to understand mobility and infection spread with privacy, how to do contact tracing with privacy is a whole open question. Lastly, the economics is a complex thing. So for example, we can say that, okay, reduce the most mobile people, but maybe these are essential services. Maybe they need to move. How economics and essential services interact with mobility is something we need to understand better. So the final punchline of all this is that we need more calculated strategic interventions instead of the general lockdowns that we have been doing. And these sort of calculated interventions are likely to control the pandemic reasonably well while not spoiling our society too much. Thank you. I think I should stop sharing. Did I stop sharing?
Thank you very much.
I'm sorry, I'm trying to figure out how to stop sharing my screen.
You stopped sharing your screen, so
I
everything is
did.
good.
Okay, very good.
Thank you very much. If there are any questions, maybe you can raise your hands, or we're not that many people. Maybe just activate your microphone and ask your question.
Yeah, I had a question, Rick. This is Vaishak here. Did you come up with kind of a concrete something, say a causal model of what's happening? I mean, it seems that you did these targeted interventions, and then you plotted the results of it, which is of course quite informative. But I was wondering if you tried to analyze what kind of features influence or have dependencies with other features, and try to see if there's some kind of causal relationship that could be established.
Yeah, not yet. Maybe we should discuss that how to do that in this case. Yeah, we don't have that sort of deeper analysis yet, and that is something that absolutely needs to be done. Yeah.
And is there a sense that there's something in the literature that people are trying to do this, or is this relatively?
In this case, no, I don't think so. So all the stuff that we saw tend to talk about this sort of infection spreading at a very aggregate scale, that lots of people moving causes more infection, clearly. Even then, I don't think they did a causal analysis. They did a correlation analysis. And what we did was, like a much more fine-grained study, right? We took movement of individual people and stuff. And in that case, definitely there's nothing. At least nothing yet.
Okay, I think Ram has his hand up.
Yeah. So very nice talk, Rick. Thank you. So one question that often comes up when people are trying to do modeling of this kind, especially when you're trying to answer a question about a counterfactual, I mean, not quite with a causal model, but just asking if you had done this, then this would have happened, is how much do we trust the model to extend to that case? And in particular, how much do we trust the human behavioral aspect of the model to extend? Do you have any thoughts on how that came up in your analyses?
Sorry, I didn't quite understand the question.
And I'm asking, so when you're generalizing from what you have seen to interventions, so potential interventions, right? So we're trying to understand if you had done this, then you would have seen something like this, or you would get a bigger benefit if you close this or don't close this. And I'm trying to ask, the fact that people might not behave in one situation as they do in a different one.
Yeah.
So we know that those effects have been salient in some other models, but how has that played out in your studies?
We did not do any of that, which is one of the, I should have pointed this out in the slides. Yeah, that is one of the weaknesses of this whole thing. Basically, the problem is that if you close one popular venue, people might all go to a different one, and now the less popular venue now becomes the popular venue, right? And yeah, we have actually no idea of that. Yeah. Oh, your question actually reminded me something. So Vaishak, I saw a talk by Devavrat Shah about this sort of counterfactual argument about lockdown actions. It was not specifically about the mobility type things, but he was doing this sort of study of what could have happened if US had done something similar to, let's say, what Europe had done and that kind of stuff.
Right. So this is he's at CMU, right?
He is at MIT, I think.
Okay. Yeah. Right. Okay.
Yeah. So I don't think they have done a lot of study on this, but what happened was that they were doing some causal things and this sort of causality analysis things, and then this COVID thing came up, so they just did an application of their techniques on this stuff, but possibly there is a lot more to be done.
Right. Yeah. So interesting. Yeah.
I can send you the link to that talk later if you email me. Yep. Okay. Anything else?
Okay. Any other questions?
Okay. Thank you.
Otherwise, I have a last question as well. So do you think it would be possible to also investigate things that they are currently doing, such as social distancing on these models as well? How that would influence like popular venues, for example, or highly mobile people?
The thing with social distancing is, there are two things in the model, right? One is that people are moving, and let's say some of them are carrying infection. Then if they come close to somebody, they transmit the infection with some probability. Then they keep moving their way. Okay, that is how this simulation works. And what social distancing does is that it changes this probability. Okay. Of course, if you can, for example, change all the probabilities or some of the probabilities, the overall spread of infection would be smaller. Although the general pattern that we saw, that the hubs are critical, I believe will still hold. The reason it is difficult to say something specifically about social distancing is that it would change this probability. and we don't know by how much it will change the probability. That seems to be, if someone can tell us by how much social distancing changes the probability of one person infecting another, then it can be put into this model, and then we can see how much difference it makes. But directly, I don't have a way of doing that like by ourselves.
Okay, thank you. Thank you very much for the great talk. I think we can then hand over to Veshak, who already asked a question as well. So if you would
I'm
like,
just trying to share my screen now.
looks like it's working.
Okay, good. So thanks again. I'm switching off my video, by the way, just because I'm worried if the bandwidth gets exhausted with my video on as well. So hopefully that's fine. Thanks again to Ram and Christian for this invitation. So this is a bit different in nature from Rick's talk, in the sense that what I'm trying to do here is to kind of cover at a fundamental level some of the work we have been trying to do regarding interfacing AI and humans, and we take a specific approach to it. So what I'll try and do is provide a very short preview of some of the results we've had and some of the approaches we've taken. These are, of course, by no means comprehensive for the problems I talk about. So I'm happy to, also answer broader questions at the end of this talk. So just to, put things in context, we all recognize that AI techniques are part of very complex data sharing and data processing loop, as we saw in Rick's talk. And of course, it becomes difficult to verify, such systems, even if you consider that most of these machine learning systems typically involve thousands of features, and it's very large data sets typically used. But there is increasing enthusiasm, as we all know, certainly from the application side, to apply these kinds of models, from everything to automating job applications, looking at reoffense probabilities for criminals, looking at control choices for self-driving cars, et cetera, and the kind of very naively, the underlying question is an issue of trust. I think Ram brought this up as well. Conceptually, we can think of a whole range of problems, but here are 4 things I feel are quite prominent. There is this issue of interpretability. So how do we understand what the machine is trying to do? There is this issue of knowledge provision. How can we provide some kind of machinery so that we can inject our understanding of the domain to the system, maybe not all of our understanding, but partly provide a specification and hope that the machine is able to learn the rest. So there is that aspect. There is this issue of fairness, right, where we want to make sure that the algorithms do not discriminate against disadvantaged groups or historically disadvantaged groups, for instance. Broadly, I guess the issue is also about allowing the machine to have some kind of notion of responsibility for the choices it's making. So these are, really thorny questions. And as I said, I'm not attempting to address them in any sort of comprehensive way, but simply provide some ideas we have had to target some of these issues, okay? That's broadly some of the key concerns that are present. And what I want to talk about today is really some results we had regarding a kind of specific approach to these problems. We have tried to see these problems in a kind of unified lens, if you will. Essentially, we are arguing that what we really want is to modularize and compositionalize machine learning with human-guided knowledge. So we specifically take the approach of probabilistic programming. So if you haven't heard of it, this is a programming paradigm where classically in programming, you have variables and you assign things to these variables. In probabilistic programming, you take the approach that these variables can be random variables, okay? And I will show you how this could help you think about a very complex problem in a very simple way. And we are arguing that one way to target the computational problems with these programs is an approach called a circuit compilation. Again, I'll give you an illustration of what this looks like. So as I said, I'm just providing a teaser for some of the key challenges that come up. Then I'll motivate how we can target fairness and moral decision making using these circuits. So that's roughly the plan for today. So, to kind of motivate it a bit more broadly, I could also say that this work could be seen as sitting at the intersection of two major paradigms in artificial intelligence. On the one hand, we have machine learning, but in the 80s and the 90s, there was this emphasis on trying to provide some kind of knowledge level specification for what the system is doing. And now that's coming back in focus, now that we recognize that deep learning systems on their own quite struggle with understanding structure. So there is an emphasis right now on embedding structure in deep learning models. And this is also where the work that I'm talking about somehow fits in. So let me talk about the first problem, the problem of interpretability. Now I see this as a kind of a two-edged sword. On the one hand, we want to extract representations from a machine learning system that helps us understand what it's doing. But on the other hand, we also want to be in a position where we can provide some kind of knowledge to the machine learning system. So to kind of give a very a realistic example, but yet a simple one, is if you simply look at, for instance, data sets that talk about protein interaction, what you often see are these very complex networks. In a way, these look like social networks, right? Where you have different proteins interacting with other proteins. Now, this interaction is never categorical. So there's some kind of probabilistic dependency between these proteins. And there is also other kind of attributes that connect these proteins, for instance, to tissues and so on. So for instance, a tissue will have some protein expressed in it. You could have tissues that refer to proteins, et cetera, et cetera. So this is a very complex social network with different attributes all over. But what is happening at the bottom of this, if you get to the essence, is that you have a probabilistic model with various relations, okay? So the question is, what is the most natural way to represent this? And this is one of the challenges I would argue from the knowledge representation side of artificial intelligence. And this is kind of what probabilistic programming tries to do. Now, to give an example of what this programming language looks like, here's a very simple model of how a disease might spread. Nothing in the sense of the realism that Rick was talking about, but to give you an idea, okay? Let me tell you what's happening in this program. So it's starting off with a program, a very small set. So it's just two people. Okay, and then there are some noisy rules. Okay, it's saying that if anybody is a person, if a person is chosen at random, there is a 0.1 probability that this is the initial person. So the point of, so the person who basically starts it, I forget what the term is for this. I think it's patient zero, right? So essentially the probability that a randomly chosen person from the population is patient zero is 0.1, okay? The probability that two randomly chosen people from this population are in contact is 0.5, okay? So again, I'm just populating here this model with two people, but this could be arbitrarily many, right? And so this is provides some kind of probabilistic dependency between how people might get in touch with each other. Now, just for the sake of simplicity, I can contrast this with deterministic rules. So this is on the right-hand side, and this is basically saying that if this person is patient zero, then this person is definitely going to be infected. If I attach the probability to this, right, this would then become a probabilistic model as well. So this would be saying, even if there is patient zero, because maybe he has the right antibodies, he may not get infected, right, which is what happens in real life. There are certainly many patient zeros, most likely. And similarly, if a person is infected and he gets in contact with another person, in this case, I'm saying there is absolute certainty the other person gets infected as well. But again, I could assign a probability to this. So this is a very simple way you could specify a fairly complex probabilistic model with a few lines of the program. And of course, using this, you could query how the spread of infection has happened in the population. Okay, so this is a probabilistic program. It can be fairly complex. For instance, this is some work we did a few years ago, where we looked at these kinds of questions that appear in SAT exams, where or GRE exams, where essentially you have a question like you have a fair six-sided die, you roll it twice, okay? And you're asking what is the probability that the first roll shows a 5 and the second roll shows a 6. I should be wary of time. Christian, can I ask how many minutes are up and how many minutes I have left? Are you here?
Sorry, you have about 25 minutes left
25
until the
minutes.
end of the session.
Okay. So I'm good.
Until the end of your talk, and then 10 minutes for questions afterwards.
Good. Okay. Yeah. Okay, so so here's a question that, what is the probability that the first roll shows a 5 and the second roll shows a 6? Okay, so these are the kinds of questions you might encounter in these math exams that you take before you enter the university. And you notice again that these kinds of questions have a familiar pattern, right? You have this fair 6-sided die that you roll twice, so that becomes the probabilistic model. And the second part of the question really becomes a query. And indeed, what you can do is you can translate these kinds of questions to a probabilistic program. So what's happening in this program is that I'm saying that there's an object called a die. It has 6 sides, and again, I'm saying here, for the sake of specification, to be precise, that there's exactly 1 of 1, exactly 1 of 2. This is mainly because you could have die where this is not the case, right? So for instance, if you've played Dungeons and Dragons, you know that you have often a die with weird numbers on all sides. So this is just to say that this is a specification of die that we're picking up. And the key thing here is that on the right-hand side of this program, you see that we're taking with replacement 2 die rolls, okay? And take with replacement basically means here, if you recall from your probability theory class, it means that when you roll the first die, it doesn't mean that any side is automatically discarded for the second die. So it's a bit like if you have a bag of balls and you pick one ball up and then you don't put the ball back, then that would be take without replacement. But if you put the ball back, the second time you pick the ball up, it could be the same ball you picked up the first time. So that would be take with replacement, okay? So it takes with replacement this die, and then you can compute the probability of the question, you get the answer back. And this entire process is automated in such a probabilistic program. Again, to give you another context in which you could apply such probabilistic programs is in the case of robotics. Now, one very popular problem in robotics is how to deal with occlusion, right? So for instance, you might be looking at an object and then at the next second, maybe the object gets hidden by a pillar or a wall or whatever, and then the robot is trying to figure out where did the object go. So what we do here is a program you specify, which basically says that if you drop a smaller object in a bigger object, there is a good probability with which it falls in, okay? So what this looks like is the situation where initially on the left-hand side, the robot is kind of looking at 2 objects. Now the object at the bottom is slightly bigger than the other object. And the person drops this, puts the object on top, but of course, because it's hollow, it drops in. Now you notice in the second image that the robot can no longer see the first object, but because it has this model in the background, it's able to figure out that the first object must be inside the second object, and so on and so forth, okay? So by providing this program, you're able to augment the robot's particle filter with some additional common sense reasoning. Now, in this case, we specified this program by hand, but we have done work, and as have others, to try and learn these programs automatically from data in the first instance, and then specify this program as a bootstrapping common sense model for the robot in the second one. So these are the kinds of things we have been doing with these probabilistic programs, okay, just to provide a perspective on this. Now, as I mentioned, one of the themes we are trying to investigate is if we could provide the same kind of common computational machinery to all of these problems. And as I mentioned, the approach we take are these so-called circuits, okay? If you put your attention on the right-hand side of this slide, what you see is you have a classic Bayesian network, which says that if it's raining, it affects the sunlight as well as the rainbow, okay? And you provide some kind of probabilistic specification for this model. For instance, because rain has no parents, it has a prior probability of 0.2 being true and 0.8 of being false. And then you provide various probabilities of, of the rain being true and sunlight being true or sunlight being false and so on and so forth. What we do with these probabilistic models is we compile them to one of these circuits, which is on the left-hand side of these diagrams. And what these circuits do is that they're built up using AND and OR gates, okay? So, and recall that in an AND gate, what happens is that if you have two signals coming in and both are positive, then the output is positive 2. Whereas with an OR gate, if you have two signals coming in and both are positive, at least one of them is positive, then the output is going to be positive 2. The reason we take one of these models and we construct these circuits is that these circuits have some very nice properties that you can compute probabilistic models, probabilistic queries by doing a simple pass across these networks. So you can think of them a bit like a pre-trained neural network, except that these have very strong probabilistic semantics, okay? So these are the circuits that are somehow providing the main computational workhorse for all of these programs that we write. So we take a program, we compile this into one of these circuits, and we can use these circuits to compute probabilities quite efficiently, and we can scale it up with provable guarantees. So that's roughly the pipeline of what we're trying to do. To put this in context, as I mentioned, this is one approach for tackling interpretability, but there are many others. For instance, there is this fairly famous or infamous, if you will, plot on the right-hand side, which kind of notionally characterizes different kinds of learning techniques and where they fit in terms of predictive accuracy versus explainability, okay? I say this is notional, and it's to exemplify that it is not the case that this is an accurate comparison. This is not a plot in a realistic sense, because there is no quantifiable metric for explainability. But this is roughly how people think of this, that, for instance, deep neural networks are high in terms of accuracy, but not easy to understand, whereas things like decision trees are a little more easy to understand, but not as accurate as deep learning models. Now, what I want to say is that the work we are trying to do somehow plays a small role in this overall picture, in the sense that what we're trying to do is extract representations from machine learning models. So these can be thought of as what are called as post-hoc explanations. Okay, so symbolic models is a very small part of these post-hoc explanations, but there are many other approaches for doing this. But what we have tried to do recently in some work with the NatWest group and the Royal Bank of Scotland is trying to come up with a kind of categorization of what kind of questions determine what kind of post-hoc explanations. So for instance, one very popular explanation is called as counterfactual, where, for instance, if you apply for a loan and you get rejected, the counterfactual might say that, well, if you didn't have two other payments on your payroll, it could be that we could still grant the loan to you. So fitting these counterfactuals and other kinds of explanations in a kind of a comparative framework is what we've been trying to do. So I don't discuss that in this slide, but there is a paper we put out on arXiv recently that discusses this kind of analysis. So this provides a more broader perspective on where explainable machine learning is at the moment, so that you can get a sense of how to target questions for your data analysis. I'm happy to take questions on that as well if you're interested, okay? So I talked about interpretable representations. I talked about one specific approach for doing this using probabilistic programs. And as I mentioned, one of the computational approaches underlying that are these circuit models. What I will discuss is some work we have also done in trying to see if these circuits, which have some very nice computational properties, can be applied to other problems in ethical AI, okay? One of them is fairness, of course. This is very popular at the moment, but I will also talk about very briefly about this idea of moral decision making, okay? So fairness comes into play because as soon as you apply machine learning models to any kind of application having a social component, this could be anything from credit risk analysis, job application filtering, and of course, looking at recidivism prediction. So for instance, if you're looking at conviction rates for people, whether they would commit another crime after being convicted once, these are places where people have tried to use machine learning models, not without controversy, And in all of these cases, there is this issue of how do we balance the scales? How do we make sure that historically disadvantaged groups don't continue to be discriminated by these machine learning models, okay? That's kind of the context in which these kinds of questions come up. Very briefly, if you're not familiar with the literature, the key idea here is that you want to construct algorithms that are fair with respect to what are called as protected attributes. Okay, these could be anything from ethnicity, sex, sexual orientation, age, nationality, marital status, right? But you have to also be careful that these could be somehow influenced by proxy variables. So for instance, even if I hide your gender, it could be that your school kind of gives an indication that you went to, say, let's say an all boys school or an all girls school, and that would kind of indicate that your gender is male or female. You have these proxy variables which also have to be taken care of, and designing algorithms that somehow prevent the applicant from being discriminated based on these attributes is kind of the main goal of these algorithms. Unfortunately, after the last few years of looking into this, computer scientists have come up with multiple and somewhat often mutually exclusive definitions of fairness. I'll just give two examples, but then talk about the work we have been doing, okay? So one very classic example is this idea that the algorithm simply shouldn't use any of these protected attributes. This is referred to as fairness to unawareness. So the machine learning model simply is unaware, okay, of these protected attributes. Now the trouble with that is that it might prevent the algorithm from learning direct bias, but it doesn't prevent the algorithm from picking up indirect bias, as I mentioned, from proxy variables or other kinds of dependencies. So, you know, this kind of idea, even though it's attractive from an intuitive point of view, it has received criticism. Kind of another idea, which is roughly to balance the scales, is to kind of say that, well, among the people who would be considered, you know, positive or labeled positive in my machine learning model, I should not discriminate between the genders. Okay, so this kind of looks like the right equation to use for something like job applications, but interestingly, if you apply it to something like reoffense probabilities, it turns out that it can unfairly penalize women. So because women comprise of only 10% of the incarcerated population in the UK, and if you're trying to balance the scales, you might force some female candidates who are with no likelihood of committing crime to be considered risky of committing crime just because you're balancing the scales. This should potentially give you a flavor for why this issue is so thorny when it comes to coming up with a formal definition. One approach we have taken, which is a very simple approach again, is to kind of consider the idea of backing out the contribution of this protected attribute. What that means is that imagine you could eliminate all the protected attributes as well as the proxy variables from your data set, and you train the model completely based on that, okay? Of course, you could do it two ways. You could remove it before training, or you could remove it after training, okay? And then the advantage of removing it after training is that you mitigate any concerns about the model, again, reacquiring these dependencies on training, okay? So you could contrast these two approaches. We kind of tested this on this very popular data set, which is horrendous. Basically, it shows that even though in the case of credit scoring, so to consider whether this person is good for giving credit or bad for giving credit, even though the proportion of the data is that men is substantially more than women, the women are disproportionately considered bad for this credit score, okay? So what we do is, we kind of look at the classification accuracy when you use these two techniques, and you kind of see that you still get you can still recover the classification accuracy as the old model. So this is in the case where you have unfairness, that's the blue one. You have the fairness with unawareness, which is the red one, and you have the two possible ways of removing the contribution. And you kind of see that the performance, at least with respect to a certain model, remains fairly standard. But what you also see is that when you're looking at the disparate treatment between the genders, we have almost eliminated the treatment for certain models. So for instance, in logistic regression, there is a very small probability that there will be disparate treatment between the genders. So this is a way you're trying to balance both scales in a way. You're trying to keep accuracy high, but you're trying to make sure that you don't continue keeping the disparate treatment between the genders or sexual orientations and whatnot. So this is the kind of thing you want to achieve with your model. There are many other ways of doing this, but this is just to give you a flavor of the kind of thing we're attempting. And again, the key point we're trying to make here is that by using these circuits, you have a very strong probabilistic semantics of what the model is doing. So in some sense, it becomes interpretable because you can ask it probabilistic questions. And moreover, because of its properties, it turns out that this can scale very well. So it can, it provides provable guarantees in terms of computing these probabilities. So that's a way we're trying to bridge theory and practice in what we're trying to do. It looks like maybe I just have 5 more minutes, or at least I want to leave time for questions. So I will very briefly cover a very similar in spirit approach we have taken also for this question of moral responsibility. Okay, and again, the context in which this comes up is things like the self-driving car, but using this very contrived and I guess infamous example of the trolley problem, where you have a trolley going on the main track. If you are the person next to this switch, and if you don't click the switch, the trolley is going to be on its path to kill 5 people. However, if you click the switch, it would move, it would change tracks and kill 1 person. Okay, so this is an infamous problem because it's so widely studied. People are getting bored of this example now, but nonetheless, it raises some very interesting challenges. Okay, so for instance, there is some regulation coming out right now that the driverless car should always opt for property damage over personal injury. But imagine yourself if you're a student in such a car, and the cost of property damage is extremely large, but chance of personal injury is very small. Would you be willing to accept this regulation? That's because it could be that you end up paying an expensive insurance premium for such a problem, for such a regulation if deployed in practice. Similarly, if the regulation came out that it should always prioritize the life of the pedestrian over the passenger, the question is, would you be willing to be sitting in such a car? Right? Now, it is possible that we will always want to defer to a human expert, and you want to hard code some choices, but the problem is that in many time-sensitive scenarios, this may not be possible. So we need to think about this a bit more. Of course, the situation is a bit different if we are only dealing in a situation with driverless cars, right? Because then we could imagine some kind of distributed protocol that would ensure everybody is safe. The broader question, nonetheless, is that do we want to be in a position where machines should be thinking about the choices it has? Okay. I'm not going to go into too much into detail, but just to say that the question of understanding this idea of evaluating consequences is by no means trivial. It raises a lot of interesting challenges at what it means to be blameworthy. What we have done is we have kind of modeled such equations, not just the simple one, but a number of other problems. And we have constructed a kind of causal model for these problems. And what we do is, again, as I hinted, we construct a circuit based on which we can provide decisions for what the system would do. Okay, so we construct these circuits based on which we can answer what the system would do, and we kind of run some comparisons against some surveys that we did. So for instance, this is a situation where you have your best friend on the main track, and the question is, would you pull the switch and kill whatever is on the alternative track? And for instance, you notice that if there's one person only, most people would be willing to save the best friend's life and flip the switch. On the other hand, if you have, say, 100 people, people might even be willing to sacrifice themselves and stop the tram from going forward. we kind of show that based on these surveys, we're able to reconstruct roughly what the people are willing to do in this case. So we're able to somehow reconstruct the ethical model of the people's decisions at this point, which can be seen in some sense as a kind of reflection of the majority of responses, okay? We also can kind of show that the cost we attach to actions roughly is proportional to the survival rate of people based on these surveys. So what does all of this mean? It means that in some sense, there are some problems here. On the one hand, we are attaching numbers to people's choices when it comes to very critical decisions. This is of course problematic, but it's not uncontroversial, okay? So for instance, there is a lot, everything from insurance premiums to deciding when to service an elevator to service a train, people are often manipulating such numbers. So the point I think here is that it's not, this model is not meant to be prescriptive, but it's more like a reflection of the majority. And this again is problematic, right? Because as we see in society, we do not have common values. People disagree significantly on issues across race, gender, culture. And so the question is, if we are trying to get to a kind of alignment between ethical decision making and what humans do, we don't have a good recipe for doing this, okay? More broadly, I think the challenge here is that AI is often not legible on the people on whom it's acted on, and often correlation amplifies biases and inequalities, and we don't have a good way to really address this. So what I would like to conclude with is that there has been a lot of exciting progress on trying to apply AI to these kind of socially rich scenarios, drawing on things like probability theory, causality, and so on. And although we have some ideas on what these models would look like, there's much more to be understood in terms of the nuance when these models are deployed, specifically because we build these models based on numbers, but the decision making in the real world is often far more complex. And this goes back even to something like explainability. We still don't have a very rigorous metric for explainability. So this kind of shows that there are some challenges when we think about AI being deployed in society. Okay, that's it from me. I'm happy to take any questions about some of this work that we did or any other questions you have. Thank you very much.
Thank you very much for the great talk. If there are any questions, you can just unmute your microphone and ask, or raise your hand. In the meantime, while people think about questions, do you have an idea or a notion of how explainability and trust are linked? Like if the explainability would go up, would trust go up proportionally, or what is your experience on how these two are linked?
Let me say that there is some work linking explainability and fairness. Just to very quickly see how that could be done. If you in my slides, I mentioned that one approach to fairness is to back out the contribution of these protected variables. So if you pre-process your data, get rid of the protected attributes, then you would get essentially a fair data set, a data set where you cannot pick up on inequalities. And you could now use one of these post hoc approaches to explainability on top of that, right? So you can connect fairness and explainability. Now, coming to trust, I think trust is a much more complex issue because there are many stakeholders at play here. I mean, if we are strictly speaking about trust between, say, a data scientist and, say, a machine learning model, you could imagine that indeed there is some kind of proportional relationship between explainability and trust, right? So the deeper the data scientist is confident about what the model is doing, he can be surer about the kind of classification accuracy he's getting and the model he has trained on in that very limited setting. But if you are thinking of machine learning in the wild, where you're not just talking about recommending books on Amazon, but say using this for some more complex decision involving, say, a robot, then obviously it's not sufficient to simply look at those stakeholders, right? You have to think about the stakeholders who might be lay people interacting with the algorithm, completely unaware of the chain of decisions that led to that. Of course, explainability helps in a little bit, but there's also kind of some concern there. So, for instance, when I think about post-hoc explainability, there has been some recent work to show that these models could be fooled. Okay, so you could construct adversarial examples and tell these models that that this and that is happening, and the model doesn't pick that up when it provides the explanation. Now, this is obviously problematic. I mean, we do not expect maybe adversaries in, let's say, a domestic robot helping disabled people, but you never know, right? So in that case, I'm not sure. I think explainability helps a little bit to kind of get a sense of where the model is basing its decision on, but I don't know if it provides broader inspections necessarily for trust as a whole. That's perhaps also connected to this work that Ram was mentioning, this project we're involved in, where we're trying to understand how trust factors in from the regulatory and the legal perspective all the way to something like some verification tools that people in computer science deploy. How does a chain of reasoning go from top to bottom and bottom to up as well, to kind of get a sense of it? But it is a very thorny issue.
Okay, thank you. Any other questions?
So I have a question, Vaishak. So this last thing that you were showing, that your model kind of manages to guess what people would say in a particular ethical scenario. So it seems that if we can do that, so let's say if we do something like that, we have models that kind of replicates people's behavior. Then there seems to be this issue that if we ask about the explainability of causality of those models as to why did the model do a certain thing in a certain place, that is like going to the question of then why did those people on whom the model was trained do something? And
Yeah.
in my mind, that seems like a whole big mess, but maybe there's a better way to look at it. I don't know.
Yeah, I guess, I mean, in some sense, yeah, it's an interesting question, isn't it? I think the trouble here is that, in most cases, again, I don't speak of all the state-of-the-art approaches coming out of the explainable AI literature, but most of the common techniques that we see are only able to tell us something like, this is the decision boundary where certain things happen, right? Now, there is some kind of implicit what do I call it? Implicit flow from that thing to an action that the robot does.
Mm-hmm.
And so I could imagine that, in fact, you could backpropagate in the way you're suggesting, right? So you could say, well, if this is the action you took, what was the reason you took this decision? And it would say, well, the rules I have extracted from my data basically say that if I see a red light in front of me, I'm going to apply the brakes. Mm-hmm. Right, so in some sense, you could inspect that reasoning by coupling these two approaches, and it would seem to me completely reasonable to do that. You could criticize, so it can happen that if you train the model on some data with the distribution that is significantly different from the real world, right? Let's say in the data that you have trained the model on, the robot actually applies the brakes when the light is green. Mm-hmm. This could also provide a way to cross-verify, right? You're saying, so the rules you have learned do not agree with the intuition we have. So we need to provide more training data. So there is a way you could kind of connect these two things to make the system a bit more robust. But these are all, as you point out, different challenges in machine learning, trying to put them together, kind of opening a can of worms. But maybe we don't have a choice because that's the nature of these systems.
Agreed. Yeah.
Yeah.
Any final questions? Okay. I think there are no more questions. Thank you both, Rick and Vaishak, very much for your presentations. And thank you everybody for attending, and thank you Ram for the introductions in the beginning. And I think we can close the session. And I hope you all enjoy your lunch break. And then at 1:15, there's the next program point on the agenda. So please rejoin for that. Thank you very much, everybody. Thank you very much, Rick and Vaishak and Ram. And see you soon.